You ever get the feeling that the universe is following a hidden rule book? You know, some single, elegant principle that's running the show behind everything from colliding galaxies to just catching a ball? Well, there is. And today, we're going to pull back the curtain on one of its most important chapters, the science of momentum. Just picture it, a firework bursting across the night sky. It's this beautiful, chaotic spectacle, right? Hundreds of fiery bits and pieces erupting outwards, flying every which way. On the surface, it just looks like pure, unpredictable chaos. But what if I told you that explosion follows the exact same rule as a perfectly calculated billiard shot, or a blistering tennis serve, or even a massive rocket launching into space? I know it sounds impossible, but a single really elegant idea connects them all. So to figure out that connection, we have to start by digging into that fireworks secret. See, underneath all that beautiful chaos, there's a single, powerful principle doing all the work. To really get it, we need to think like detectives for a minute and gather a couple of crucial clues. And our first two clues? Well, they happen to be two of the most important concepts in all of physics: momentum and impulse. So let's get to know them. Okay, first up is momentum, which physicists like to call P. It's really simple. It's just an object's mass times its velocity. The easiest way to wrap your head around it is to think of it as mass in motion. The more mass something has, or the faster it's going, the more momentum it's packing. It's basically a measure of how much oomph you need to stop something that's on the move. And here's what's so wild. Totally different objects can have the exact same momentum. A heavy bowling ball just kind of rolling along can pack the same punch, that same mass and motion, as a tiny little rifle bullet screaming through the air. It's all about that trade-off between how heavy you are and how fast you're going. So our second clue is impulse. Now, if momentum is mass in motion, you can think of impulse as the thing that changes it. It's not just about how much force you use, but for how long you use it. Think of a quick jab versus a long, steady push. They could both deliver the same impulse by balancing that force and time. If you were to graph it, the impulse is just the total area you see under that force versus time curve. Okay, so we have our two clues: momentum, the state of an object's motion, and impulse, the action that comes in and changes it. Now let's connect them, because this is where the real magic happens. This connection is called the momentum principle, and it's incredibly powerful because it's so simple. All it says is that the change in an object's momentum is exactly equal to the impulse you give it. That's it. An impulse causes a change in momentum. It's this simple, direct relationship that works everywhere, for everything. Let's make this super visual. So imagine a ball moving along to the right. It has a certain amount of initial positive momentum. Let's call that its starting score. And now, bam, we apply an impulse, we hit it from the other side, applying a force that pushes it back to the left. This creates a negative impulse, which is going to get subtracted from its score. So the final momentum is just what you started with, plus the impulse you added. In this case, that negative impulse was strong enough to completely reverse the ball's direction, giving it a final momentum in the negative. This is the momentum principle in action. Your initial state plus the interaction equals your final state. Simple. Now, you might be thinking, hey, this sounds a lot like work and energy, and you're not wrong to see a connection. But there's a really key difference. Work is a force you apply over a certain distance, and that changes an object's kinetic energy. Impulse, on the other hand, is a force you apply over a period of time, and that changes an object's momentum. They're like two different sides of the same coin. So we've seen how momentum can change. But the most powerful idea, the master key to our whole firework mystery, is what happens when momentum doesn't change at all. To unlock this idea, we need to talk about an isolated system. Don't let the name scare you. It's just a collection of objects, like two billiard balls about to hit, or a rocket and all its fuel, where all the important forces are happening inside the system, between the objects themselves. There's no major outside force messing with the whole group. And when you have one of these isolated systems, something incredible happens. You get the law of conservation of momentum. This is one of the most fundamental, unbreakable laws in the entire universe. It means that no matter what crazy stuff happens inside that system, collisions, explosions, you name it, the total amount of momentum in that system stays exactly, precisely the same. To put it even more simply, the total momentum you have before anything happens is the exact same amount you have after it's all over. Yeah, the momentum can get shuffled around between the different parts, like billiard balls swapping some speed, but the total amount in the system never ever changes. It is conserved. Okay, we have our master key. Now let's use it to unlock the secrets of all those collisions and explosions we were talking about.
So, in pretty much any collision, as long as it's an isolated system, momentum is always conserved. But we can look at two extremes. On one end, you have a perfectly inelastic collision, like two train cars coupling together. They stick. In that case, only momentum is conserved. Some energy gets lost. But on the other end, you have a perfectly elastic collision, like two billiard balls bouncing perfectly off each other. There, both momentum and mechanical energy are conserved.
And this, right here, brings us all the way back to our firework, because an explosion is just a collision running in reverse. Instead of things coming together, they're flying apart. But the rule? The rule is exactly the same. The total momentum of all those flying pieces has to be conserved. A rocket launch is the perfect example. Before it takes off, the rocket and all its fuel are just sitting there. The total momentum is zero. Then it fires its engines, blasting hot gas backward with a huge amount of momentum. Well, to keep the total momentum of the whole system at zero, the rocket has to gain an equal and opposite amount of momentum forward. That's it. That's rocket science. And it's all built on this one beautiful principle. So, in the end, you see, conservation of momentum isn't just some clever formula for physics class. It's a reflection of something much, much deeper, a fundamental symmetry of the universe. It's a sign that the laws of physics work the same here as they do on the other side of the galaxy. This rule isn't just a calculation, it's a core part of that hidden rulebook the universe runs on. From a chaotic firework to the precise launch of a rocket, everything follows this one simple, unchanging rule. Which kind of leaves you with one last thought, right? What other chaos in our world is just a simple, elegant rule waiting in disguise?